Hi, my name is Jack Huang. I am Life Sciences, and this is my BlueSky proposal. There are many nearsighted people in America and around the world. Here in the United States, around 1/3 of all people are nearsighted. And in parts of China, up to 80% of children may be nearsighted. Nearsightedness is not a huge problem in society, but it does affect a lot of people. And many people have been turning away from glasses and using contact lenses. Contact lenses are great because they're convenient, and you don't have to wear glasses. But because they sit directly on your eye, there's an increased risk of infection associated with contact lens wear. A primary driver for this infection is protein and lipid attachment to these contact lenses. These proteins come from the tear film that is naturally present in your eye. But when there is a plastic contact lens in your eye, the proteins that are naturally present in your tears, which are usually antibacterial and have other desirable properties, can attach to these lenses, and in the process, they will denature. And not only will they not be beneficial to your eye, they can also be harmful. These proteins can provide a breeding ground for bacteria such as Pseudomonas aeruginosa to attach, and this can lead to infections and microbial keratitis in contact lens wear as well. And so for my project, I would like to propose to examine what properties of the contact lens polymer allow these bacteria and other microbes to attach. And the way they attach is through protein adhesions. So I'm looking at the characteristics of a contact lens polymer and how much protein attaches to these lenses. And not only do we need to look at the absolute amount of the protein, but we also need to look at the conformational state of the protein. Because a protein in its native state can have desirable effects versus a protein, if it is denatured, can elicit an immune response from the body itself in addition to providing a breeding ground for bacteria. Many concepts that we learned in LS1a apply to my project. One is we learned a lot about protein denaturation and the hydrophobic effect. Usually a protein is immersed in an aqueous environment, and the hydrophilic residues of amino acids are on the outside. But when this protein is placed into a more hydrophobic environment, there's an effect that has the hydrophobic amino acid residues, which are usually on the inside of the protein, want to come out to the outside. And this is the case with contact lenses in the sense that contact lenses are more hydrophobic these days than water usually is, and this is what causes the denaturation. We used to have more hydrophilic contact lenses than we have now. But one issue with more hydrophilic contact lenses is that, one, because they're hydrophilic, they absorb more protein onto them. And so you have this balance between more protein or less protein but more denatured protein is an issue. And also the hydrophilic contact lenses, they were called hydrogels before. And one issue with those is that they're not very permeable to oxygen. So you have an issue where if the eye you're wearing a contact lens doesn't get enough oxygen, that can lead to a whole host of other issues as well. So it's not a simple equation of just altering the hydrophobicity, but there might be some way that you can ideally have both the oxygen permeability and also deter the protein absorption onto the lens. So I'm not a materials scientist myself, but there's been a lot of buzz in the scientific community lately about nanotechnology. And I'm sure if we get materials scientists introduced to this topic, they can help us develop some sort of technology that can achieve the best of both worlds.